you.
Probably worth all dial in on the phone.
Yeah.
Wonderful. Thank you.
Your wife's right. Front row. Thank you,
It's
Sarah.
only really important. He was going to switch with it to see if you noticed.
See if yours
I think
works.
I might.
See if yours works
He
better.
did swap me too. Good try.
Sorry. I didn't know you actually did it. I'm not as fast as Scott.
I have a little hint.
Yes, I know on this side.
But you saw into his evilness before I did.
No, he just told me.
Yeah.
Otherwise, believe me, I haven't finished my part.
I stopped at Pete's on the way in, so it's already kicked off. There you go.
Okay, so good morning. So interestingly, yesterday, the Journal of Science published an online article called "Who is the Michael Jordan of Computer Science?" Reporting on work from the Allen Institute for AI in Seattle, I guess Ora Netzioni and students who have developed a system to try and more deeply understand computer science publications. So looking at things like what the sections of the paper are, and importantly, what the tone is of other scholars who reference a paper. So based on that, they recently extended the capability to basically create an influence network, trying to determine which researchers have the most true influence on their field. So they ranked everybody in computer science. And it turns out that the Michael Jordan of computer science is with us today. Michael Jordan is at the top of the list. They very flatteringly called him Michael Jordan, a pioneer of AI that few outside his field recognize. Which I thought was sort of strange because he's a member of the National Academy of Science, the National Academy of Engineering, the American Academy of Arts and Sciences, and of course within his field, I mean basically anybody remotely involved with machine learning, data mining knows who Michael Jordan is. He's well known for pointing out connections between machine learning and statistics, variational methods for approximate influence, Bayesian, popularizing Bayesian networks. If anybody's ever used the LDA, latent Dirichlet allocation model, Michael wrote one of the seminal papers on that. So we're very pleased to have him here today. So let's give a warm welcome to Michael.
Okay, thank you, Peter. It's a pleasure to be here. I didn't actually know all that stuff.
Hey, Wikipedia. Which also already says something.
Right, okay. It's a pleasure to be here. It's been at least 10 years. I think my first game to Berkeley came here. So before all the big data stuff, I'd come here and talk about who knows what. But so today I'll talk about, I think instead of saying big data, said data science. I think it's kind of the academically more respectable word, even though it comes from industry. So this talk's going to be a little bit for everybody. There's going to be some kind of high-level perspective, some conceptual framework, and then some actual math at some point. So hopefully some part of it everyone will like, and no one will like all of it, I'm sure. At the end of it, there'll be a little math because there's a brand new result that I'm really excited about that I want to show you. So you're a little on the theoretical side, you'll be interested. So let me start with kind of a little bit of pseudo-history, self-centered history. Where I started hearing about data. Of course, I've been in statistics and computer science for my whole career, so it's always been obviously, yes, you should be working with data and algorithms. But where did it become clear that it was going to become such a trend? So at least for me, it was more from the science side than the technology. So you saw the, say particle physicists gathering huge amounts of data. And I'm always interested in why they're gathering the data. What's the inferential question for me? It's not just that they gather data and there's a huge volume, velocity, and all that kind of descriptors of data. That's fine, but why did they gather data? Well, in this case, the inferential question was a hypothesis test. It was, is there a Higgs boson or not, or things like that. Okay, so it's literally a 1-0 test. Why do you have to gather so much data to do a 1-0 test? right? Well, they're out of energy regimes which are never been explored before, and out in those regimes, all the noise fluctuates a great deal, what we call nuisance variables in statistics. And so the null hypothesis is a particular density curve of some kind. The alternative that there is in each is on exactly the same density curve with a little tiny extra blip somewhere, right? But the noise is so huge that to actually reliably see that blip, you have to gather huge amounts of data, all right? So hypothesis testing, but in a regime with lots of nuisance variables. Next kind of phase was more exploratory. So in statistics, we have confirmatory, that's hypothesis testing, and exploratory. So exploratory, the astronomers, the genomicists, et cetera, just started gathering huge amounts of data, not to test a classical hypothesis. They didn't have any hypothesis. They were trying to find new hypotheses to study. All right, so now the inferential, the volume and velocity of data is the same. It's huge and lots. But completely different from an inferential point of view. They're trying to return out of the billions of possible hypotheses you could study, a few thousand that are worth studying further. Okay, so completely different error profiles and so on. Okay, so the next phase is the one we all know and love. Internet companies especially, gathering huge amounts of data. What's interesting about this is, again, not the volume velocity of the data, but the inferential questions. The inferential questions were now individualized or personalized. Everybody was doing personalized search, personalized medicine, personalized everything. Why can they talk about personalization? Because they have data about every person, roughly. Of course, now they have new inferential questions. First of all, you can't just serve 95% of the people well. You have to use what we call the L-infinity norm. You have to serve essentially everybody well, because if 5% of the people are getting bad service, they're the ones who complain and your service looks really bad. All right, so that's one thing. The other thing is that you've got power loss. You've got huge amounts of data on some people, very little on other people, and you still want to serve everybody well. So inferentially, completely different questions than the first two are now arising, and these are the ones that we're still facing this day. And some of the other inferential issues that come up are the heterogeneity, the unknown sampling frames. Did I get too much of one subpopulation, too little of another, and so on, and compound loss functions. All right, so that's just kind of there is data and there's inferential questions, but of course now you have to put this on a computer and make algorithms run. It has to be done at scale. So now there's all the computational issues. So this is kind of like at least 10 years ago, this kind of was clear to me. It was like, I just spent the next part of my career. It was sort of intellectual issues, and it wasn't just building systems. So I got involved in starting what's called the AMP Lab, where the issue was just to build systems and see what happened. And that's great. But to me, it was more about what are the intellectual issues, what are the conceptual issues, what are the mathematical issues. So that's what the talk's going to be about. So let me try to say this in a different way. I'm going to envisage now a student who's just graduated, an undergrad student from Berkeley, who's I'm having a conversation with, and they're heading down to the Silicon Valley to start a job. So on day one, their boss says to them, I need a big data system, whatever that means, that will replace our classical service with a personalized service. This happens all the time. All right, so the student says, well, I think I can do that. The classical service was a particular box with some parameters that were set with some data, maybe some optimization procedures. You just had one box for everybody. Now I'm going to have 100,000 boxes. So I just got to have enough computers so I can probably start to do this. Now it gets harder because the boss says, well, it needs to work well for anybody and everybody. It can't just work for 95% of the people, as I was saying earlier. So that starts to get really challenging. How do I control errors kind of uniformly across a bunch of models? That's not what we usually do. So the student starts to worry a little bit. How I could promise this, but it'd be hard to do. But that was just the kind of statistics. Now the computer science really comes in, a hard way, which is that the service cannot be slower than the classical service. All right? It's like your Google, you've been offering search all these years and it runs at tens of milliseconds. Suddenly you roll out this great new thing called personalized search. It's better, but it's slower. No one's going to like that. You can't do that. Okay? So now how do you do that? Now we don't have engineering principles, I would argue, that allow us to do that, to control the statistical error with a budget, a runtime budget. We don't have that engineering field that exists that can, So what do? You hack, you build a system, you hope it works. If it doesn't work, you get some more computers, right? And hopefully parallelism will kick in, maybe Moore's law if you wait a while, but parallelism. But if it doesn't, you don't know what to do, you're at a loss. And there are many situations where it doesn't. So people build systems and it's not clear that it's working. All right, now it gets only worse. And here's the one that actually gets me really interesting to me, which is that today we've got petabytes of data. That's how we're able to do this personalized service. But in 10 years, we're going to have way more data. Isn't that great? Okay, the answer should be, yeah, it's great because I got more of the resource that I'm using to build my system with. But the computer scientist in my student list says, wait a minute, all the algorithms I know are like n cubed or n squared or np or n log n. They all grow in the amount of data. And I'm trying to give you a runtime budget that stays fixed. How can I do that? I don't know, would be the honest answer. And none of us know. All right, so I like to use the metaphor of human build things for centuries or millennia. So people built buildings and bridges, and they kind of learned crafts for how to do that. And they built lots of builds of bridges, and things kind of worked. People went across them, but often enough they fell down, and a lot of people died, and it was kind of problematic. And we're at that same stage with big data systems. We're able to build some, and we're able to put them, but we have no civil engineering. We have no field that has emerged. So sort of, here are the principles, here's the guarantees I could give, here's the, if the situation is this, here's how I do it. We just don't have anything like that. So I think that's decades at least to build. I don't think we're just beginning this. So it's an interesting time. All right, now of course it only gets worse. The real world is full of other kinds of externalities. So all this data was collected by somebody. So there's going to be privacy concerns, for example, and there's going to be administrative concerns, all kinds of things. You got to take that into account as you build your data analysis system. You can't just view it as maybe. All right. Okay, so let's dig into some of these things. So the next thing I want to point out is that there's kind of two styles of thinking that go into building systems like this. This buzzword of computational thinking is often been used. I think it was kind of Jeanette Wing at NSF that promoted it a lot. That computation is much broader than you ever thought. It's not just computer programming. It's, that style of thinking should be everywhere. And that was a great thing for her to do and others to do. But at some point they started to carry it a little too far to my taste. They said, well, also all of statistics is just algorithms. It's computing. It's part of computational thinking. Right? So I'm going to try to argue that's not the right way to think in the next few slides to kind of convince you that this whole other area called inference is 300 years old, and it is its own style of thinking. And blending the two is not easy, and it's not hard. You can't just put an umbrella around it. You have to think to blend them. So computational thinking, what do I mean? A good first semester class at a good university. You talk about abstraction, modularity, scalability, especially scalability, robustness, and so on. Inferential thinking is maybe less familiar if you're a computer scientist, but it's always about trying to think about what's the real world phenomena behind the data. How was the sampling pattern that gave rise to the data? So I'm trying to talk about the phenomena behind the data, not just the data itself. Often my database colleagues, it's just about the data itself. They're not trying to think about what gave rise to the data and what's the other things I could say about the thing that behind the data. So I'll try to make that clearer as we go. So just to kind of push on this a little bit more, people often will build a database system that can do statistics. It can do regression, or it can calculate means or medians or something. They say, well, I'm doing statistics in a computational setting. What more do you want? So I'm going to try to argue what more I want here in a couple of slides. Last slide on this kind of philosophy, which is, so I've become more of a theoretician over the last 20 years now that these issues have been coming up, and I think they have to be solved by being a theoretician, trying to get principles and rules of thumb and so on. And it's hard because, so core statistical theory, it's called statistical decision theory. There's hundreds of thousands of papers written about it. It doesn't have a place where you have the word runtime appear. It's just not in the theory. And when you see the word runtime in the statistics journals, it just doesn't appear. Right? So there are things like number of data points, or, other complexity measures, but that's not the whole field of computer science exists to take number of data points in and turn it into runtime. Right? Similarly, on the CS side, we have core complexity theory of all of its variations. And you'll look in vain to find the word risk. You'll optimize over all kinds of other quantities, worst case tree metric errors, approximation ratios, and all sorts of other things. You won't optimize over statistical risk. So it's kind of missing the core concept you need on the other side. So these are challenges. So let me say a little bit about what we've been doing in my group for the last 10, 15 years. I'm just going to give you some vignettes, really. So I'm not trying to sell anything today. Here's our fantastic thing that does everything. It's kind of I'm trying to sell this kind of thought experiments. How to put these pieces together and try to build structures, theoretical structures that lead to systems. And so that's what I'm going to try to do. So I'm going to give you some examples I just think I can do in 10 or 15 minutes. One of privacy, one with Shannon style communication, but done in a different way. And then I'm going to talk about this perspective, this new work, returning to a previous perspective on variational methods. Yeah?
So where would you put prediction of
I think of it as inference. On my next couple of slides, I think you'll sort of see what I mean by that. It's out of sample. It's not just the data itself. It's something else. So let me get to my next couple of slides. When I get to privacy, you'll see what I mean.
Yeah, so Michael, you talked about computational and also information.
Yeah.
So then you said computation is about algorithms and all that, but when we go to the deep learning, it's less about algorithms and more about observation, neural net stuff.
So I don't want to talk about deep learning at all today. I refuse.
Fair enough.
So let me talk about privacy. This is joint work with John Ducci and Martin Wainwright. So I think I have to tell you the story, and we're going to be relying on kind of differential privacy ideas, but that you're very familiar here. But you know, the goal, of course, is to have systems where if I'm providing you data, I can have a knob that I can turn to tell you kind of how much to fuzz up the data before you use it. Okay, so and now the main point I want to make is that it depends on the inferential problem. So if you tell me you want my genome, I say, well, what for? And you say, well, I'm studying a disease that runs in your family, and I want to make predictions about that disease. I say, great, have my data. I'll turn the knob all the way up. You say, well, I'm trying to use it to set insurance rates. I'll say, well, turn the knob down a bit. I don't really want to, you know, reveal that. I'll partially reveal my data. I do believe it's important to set insurance rates, but I don't. Or you say, no, I'm trying to sell you ads. I'll say, I'll turn the knob all the way down. Okay. So what I just did is I had a knob, and I set it depending on the inferential problem being solved. So we had to have a dialogue, you as the analyst and me as the data provider, about the inferential problem. Now I can set the knob. I set the knob, and then you collect the data. So there's this back and forth phase we've got to think about. All right. So how do we, in particular, juxtapose the loss in privacy, the differential privacy loss, against the statistical risk? That's going to be the question. That's a new question. So now let me try to make a picture that sort of hopefully will make this more clear to everybody here. So I'm going to be now a classical database person. I've got a database. It's I'm a bank. I've got, you know, people's address, their age, their height, their weight, and I've got their amount they have in the bank. Okay, and I want to do queries against that database. So I put in a query, I get an answer. I'm going to call it theta twiddle for some sort of odd reason here. Okay. Now I'm going to do private databases. So I'm going to maybe use a theory like differential privacy. I'm going to privatize the database by putting through a kernel, an operator Q that's probably random. That's going to add some noise to the database. So now that I can run the same queries against a privatized database, I can get an answer, and I can guarantee that theta hat will be close to theta twiddle, overall queries with high probability. Moreover, I can guarantee you that things like that I can't say whether you were in the original data or not, with you know how much power for that detection, things like that. Okay, so that theory, I'll say a little more about that if you don't know about things like differential privacy, but that theory exists. Okay, so now you know, let's consider this as a beautiful example of computational thinking, and think about what's not in the picture. Okay, so the statistician would look at this and say, well, behind the database there must have been some population. What is that population, and what are you trying to say about the population? And he said, well, I'm a banking guy. I care about the people in my banking. You know, who has the money in the bank and how much they have. I don't care about the people who could have been in my bank. Right? And that's true. In that situation, I don't think you should be thinking inferentially. But now let's think about another situation where the database is medical records. So I've collected a whole bunch of age, heights, weights, and blood pressures and stuff, and I've given people a drug or not, and I've seen how long they lived. Another interesting data set. I could run queries against it, right? And probably I want to protect the privacy of the people in that database. Probably. Okay? But I may or may not be interested in those people at all. Okay? They may be dead and gone, in fact. It's good medical data still. I want to use it for people who are not in the data, who could have been in the database. That's inferential. So a statistician starts with the data, right? Thinks about the queries that are going to go against that data, and then always thinks about what's the population behind the data, where did the data come from, and what was the sampling pattern critically? Okay, was it stratified? Was it IID? Was it what was it? Think about that, because your inferences would depend on it. And now you can imagine running queries against the population, and out comes an answer theta. So what that really sort of means is like a prediction. So I can ask, for someone who was not in the data, can I predict what their the lifetime would be if I gave them a drug or not? Okay? So that's an inferential setting. And now the theory of statistical inference says things like theta is guaranteed to be close to theta twiddle with high probability over the sampling pattern, over the population P, and overall queries in some family. Things like that. So that theory exists for many, many kinds of problems. And, you know, it's been decades of work to do that. And I hope you now know where I'm going. What I want is to put the two together. Okay? So now I want to think about, I gathered a bunch of data, say it's medical records, and I actually don't care about the people in the database at all. I don't care about their specifics. But I want to protect their privacy, right? And now I want to think about making inferences on the people who were not in the database, but could have been. And I want to prove that theta is close to theta hat. I don't care about theta twiddle at all. I care about theta being close to theta hat with high probability, overall Q, S, P, and query families. Right, so there's the mathematical problem that I think we should try to be solved. And to do this, you have to blend these two styles of thinking. You have to think inferentially, think about the inverse problem, the sampling pattern, and so on. And you have to think computationally about how do you set up something like a differential private database. So let me just say a little bit about blending those two theories. So in statistics, you need risk. So even when you're Bayesian or frequentist, you need risk. So let's start to get a little bit of notation here. We have some family distributions where the true distribution P lives. So script P is the family. The true distribution P generated data, and I'm interested in some, let's call it a parameter. It's just some functional of the probability distribution. It could be a tail probability. It could be, just some feature of the probability distribution. I have an estimator, theta hat, which is hopefully going to estimate theta, and I define a loss that tells me how unhappy I am if the truth were theta of P, and I return theta hat. Now, theta hat, at this point, we're going to be frequentists. We're going to assert that theta hat's random because the data is random. And so we take an expectation with respect to the probability that generated the data. So P appears twice here, and it's the same P. All right, so here, at this point, statistical theory becomes about average case. Whereas computational theory is usually it's maximum, maximum, maximum. At the very core of this, it's an average case. All right, now it's average with respect, you always in computer science has, well, average with respect to what distribution? Well, here it's clear, it's with respect to the distribution that generated the data. All right. Now, you get an object here called the risk function, so that's the expectation of velocity is the risk. It's a function of P. So if P is a one-dimensional object, which it never is, but suppose it is, then you have a curve. R of P is a curve. Now, Peter has his curve for his theta hat. He likes the median, I like the mean. His curve is here, and my curve is here. If his is always below mine, he wins for all P, so I should use his procedure. Typically, the curves cross, however. So some regimes where he wins and some regimes where I win. So Wald was aware of this, and he said, well, one of the ways to get around that problem is to at this point go worst case. All right, so take a supremum over the average of the loss. That's called the maximum risk. Okay, so that's now just a single number for a particular theta hat. All right. Now, what's the mathematics here? Well, the mathematics is that this number is a function of the number of data points n, it's a function of the dimension of the problem d, it's a function of all kinds of other statistical parameters. And so the statistical theory is to study this using things like packing numbers and Fano's inequalities and blah, 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 and get this to be something like, d divided by square root of n, or some formula that suggests how the risk will go as the various statistical parameters change. And then you get that to a user, tells them how much data to gather, when to stop, how much error they expect, and so on. Okay. Okay, so that's the story. So now let's blend this with privacy. So here's we're going to study what is called local privacy. People hold data x1 through xn. They're willing to only reveal privatized data z after x has gone through a channel q. Okay, so the data is coming from P, but as statistician at IBM can only see z and wants to do inference based on that. Okay, so here's this one picture. We've used information theoretic ideas, but we eventually kind of agreed that differential privacy was a better framework for this study. So differential privacy is just a story about the channel. It has nothing to do with the P or the queries or anything. It's just about the channel. All right. So what you do is you look at the output of the channel. I do have a little red dot.
There's a pointer right there. Yeah.
All right. So you look at the output of the channel, Z. Consider some adversary that picks some particularly nasty set to look at to sort of try to reveal things about the input of the channel. And you look at the input of the channel under two different inputs. X might be the database with me in it. X prime is the database with me not in it. If these numbers are close to each other, you can't detect whether I was in the database or not if you're looking adversarial over all possible sets S. Okay? All right, and so in particular now I have a little tuning knob here, alpha. If I set alpha to 0, I'm trying to be extremely private, that makes this be a 1, that makes this likelihood ratio be a 1, and that says you can't detect at all whether I was in the database or not because you get the same answer no matter whether I was in it or not. If I let alpha get bigger, then I'm allowing a little tube around the likelihood ratio here, and I'm allowing some discrimination for an adversary to try to say, oh, I think you were in the database. But the power to detect that is going to be small, so the adversary can assert that, but in court of law, you'd be able to say, well, your power was low, so you claim you detected me, but you can't prove that you could have detected me. So that's this idea of differential privacy, and there's been a lot of work about mechanisms and lower bounds. Okay? So what are we going to do? All we're going to do is we're going to put this brand new piece right here. So let me just go through this again. We've already talked about it, but this is the loss function. The truth was P. The statistician got to use the fuzzed up data Z. This is the risk, and that's the worst risk. And now this is the minimax risk, and that's what Wald suggested we study. Find the best procedure under the maximum risk criterion. Okay, so that's what to this day people in statistics often study, not exclusively, but. And all we're going to do is add another. We're going to make this into a constrained optimization problem. We're going to add another infimum over this externality, this requirement that you have a channel which is in the family of channels that protect privacy at level alpha. So find the best channel, given you have that constraint. That minimizes the risk. That's the story. Okay, so that's kind of easy to write down. And now the question is, can you do math with this and get a little formula out that has things in it like n and d and all the usual statistician things, but also has alpha in the formula? And how does alpha appear? So we have papers on this, and you can look at them, and the answer is going to be pretty simple. So let me give you an example showing you how this formula rises. So just to make this also concrete, let's suppose that people are coming into hospitals and they've been abusing various substances. So this person abused alcohol and cocaine and not heroin. And now we have a database of such people. And I want to infer just the underlying proportions. How many people in this city abuse the different substances? Now, why do I want those numbers? Well, for public policy, I want to know how many hospitals to build, how many people, doctors to have in each hospital, and so on. Okay? So classically, I would just get data like this, and I would take the maximum likelihood estimate. I just take sample proportions, and they would uniformly approach those true proportions. I get enough data, and I'm good. All right, but no one wants to reveal that kind of data. So how do we set this up? Okay, so here's now the theory of just doing this for now in a very stringent situation. So we're just trying to estimate the mean. That's what theta is. It's d-dimensional. We're going to do this in the L-infinity norm, because I argued earlier this is the norm we should be using these days, not L2. And we're going to be non-parametric. We're looking at all possible distributions on some compact set, not just some particular distribution. All right, so in that setting, it's actually an elementary first semester exercise for a student to do the minimax risk. And it turns out to be 1 over the square root of the number of data points. And then d appears logarithmically in the numerator. So it's a little somewhat easy exercise. And that's gotten by solving this problem without the green part here. Okay, now if I put the green part in, hopefully alpha will now appear in the solution. All right, and it does, right here. Okay, so n multiplies alpha squared. All right, and now, as I'll show you in a couple minutes, that's not just for this problem, it's for a wide range of problems we study. This is always what happens, n multiplies alpha squared. Okay, so I think it's a little law of private data analysis. And how would you use it? Well, so you come to me, you say, I want your data. I say, well, what's your inferential problem you're studying? And you tell me what it is. And I say, okay, I'm going to set alpha equal to a half for that problem. You say, fine. I multiply a half by itself, squared. I get 1/4. I multiply that by n. And now the risk is now proportional not to n, but to 1/4 n. So all I got to do is gather 4 times as much data, and I can have the same risk as I had before, and I protect your privacy. And this is before I saw the data. I can just do this. I can have this little dialogue. And I know how to set this as a function of privacy and risk and dimension of the problem. So that's the kind of theory I think we need. That's blending these two styles of thinking. Okay, so that's a lower bound. It's just math. Are there procedures, algorithms that actually achieve this lower bound? Okay, so you would go to the literature, differential privacy. Well, what algorithms do they actually use? So here's some data that you want to privatize. Well, what's typically done, not always, but one mechanism is to add heavy-tailed noise, Laplace noise, to the components of the vector. Okay, so you prove that this protects differential privacy level alpha. You also prove if you add Gaussian noise, it's not going to protect privacy. So it works, but the question is, we're not just trying to protect privacy, we're also trying to use the data to make inferences. Can we make good inferences while we're making this guarantee? And the answer is no. So the risk is, I'll show you a plot here in a minute, but our theory tells you that it's quite suboptimal to use this mechanism for this problem. Okay. So is there some other mechanism? This doesn't achieve the lower bound. Is there some other mechanism which might achieve the lower bound? And there is. So here it is. Here's the data we're trying to privatize. What we're going to do is flip a random coin, Bernoulli coin, and get a random vector v. Okay, so toss it independently for the components, and also form 1 minus v, the complement. Right, and now we're going to transmit to the central statistician the closer of v and 1 minus v to the data, with probability proportional to e to the alpha. Okay, so if alpha is 0 and I'm trying to really protect your privacy, then that's a 1 divided by 2, that's 1/2. And so I uniformly random transmit a random vector to you. I'm giving you no information, as guaranteed. And if alpha gets larger, then I am leaking information to you, but slowly. It seems kind of like a pretty poor mechanism, right? But you need a theory now, and the theory tells you that it's not a poor mechanism, it's actually optimal. Okay? So your intuition might be, my intuition is this is a poor mechanism. This is a form of randomized response. So it's been around as kind of a heuristic in literature for a long time, but it hadn't been a theory about it. So anyway, the theory tells you that it is optimal, and here's actually showing you this on real data. Here's L-infinity error. This is this data. This is sample sizes up to 60,000. And this is the add Laplace noise mechanism. You want small risk, and this is the optimal mechanism. So on a log scale, extremely significant differences. Okay, so that's all I wanted to say about this. We've been continuing to work on this problem on kind of privacy meets inference. Let me just say that some of the papers get into other statistics problems. The one I just told you about is multinomial estimation, but some of these others. And it turns out this formula arises in all cases, almost all cases, not here, but almost all cases this formula. So this is kind of a law of private data analysis. There's other laws for other kinds of privacy, but for data analysis, it's a little bit of a law. Okay, let me just in 5 minutes say something about another field, but with some more style. But answer a question first. Yes.
So for differential privacy, there's also a budget in terms of the number of queries that you can answer,
Yeah.
right?
Yeah.
So does this...
Yeah, that's orthogonal to what we're doing here, but that's one of the things I like about differential privacy is that if you query a database several times, and each time there's alpha, you do it k times, then the total loss in privacy is k alpha. And other privacy mechanisms don't have that nice property. You put two databases together, and once you make separate kind of pseudo privacy guarantees, you put them together, you know everything. So that's one of the reasons why we kind of agree differential privacy is a good place to be studying this thing. I should say, though, that in our theory, I kind of went over this kind of quickly, but D is appearing in kind of a bad way, the dimension of the problem. So it used to be log D, and then it became D log D. That's a pretty bad penalty for high dimension. So protecting privacy in high dimensions is hard, according to this theory, probably too hard. So there's one of the, it's known differential privacy is too stringent, and this is a kind of a quantitative way that's coming up. So if you really wanted to protect privacy in high dimensions, you would probably have to do something new. Yeah. Okay, so, yeah, please.
I've noticed a question about that scaling. So far you've been assuming that alpha is less than 1. Just what happens?
Yeah, that was, no, it can, so that's for the math. There's a Taylor expansion here at some point,
Okay.
and that's for the math to make that nice formula come out under that Taylor expansion. But the theory does apply to alpha being bigger than 1.
But with a different form.
There's a correction to that form. There's a high order expansion. Yeah. Under the hood there, this is kind of just Fano inequalities and counting numbers sort of stuff. So it's an information theory. We had sort of tweaks on the theory, but nothing substantially different. Okay, so let me say a little bit about compression just to give you, again, this is a vignette. This is a little thought experiment just to give you an idea of where this kind of thinking leads you. So, we're going to look at a now problem which looks very similar, that I'm going to have data now distributed over multiple computers. And the data is so huge that I can't transmit all of it to a central site. So I've got to compress. Okay, so now I'm going to have a channel which compresses x1 to z1s, x2 to z2, and so on. And now this data is small enough that I can meet my bandwidth limitation here and transmit to a central site. Okay, that's the setup. All right, now what theory do you use to do this? How did you build algorithms? What can you predict how well you're going to do? Well, didn't Shannon solve the compression problem? Then with all the algorithms developed by the various people after Shannon. The answer is yeah, if you're just worried about controlling the number of bits you're sending. But if you're worried about controlling the number of bits and doing statistical inference on the other end, no, they didn't even address that problem at all. That's not part of Shannon theory. Okay, so how can you manage communication and statistics together? Well, it's going to be exactly the same kind of setup. So we now have a new constraint. There's no alpha in the problem anymore, or you could bring that in. There's now B, which is the bit rate between here and here. So I've got to now guarantee that the bit rate is controlled at level B, and Z is the output of a channel that controls the bit rate at level B. So B comes in right here and here. Okay, so it's the same thing before, minimax risk under the constraint that you compress down to B bits. There's many ways to compress down to B bits. Find the one that minimizes the risk. That's a very natural setup. Now, again, the question is, yes, you can write that down. Can you do mathematics that gives you interesting answers? So let's do this in a particular problem just so I can show you some results. Let's just suppose that we have high-dimensional Gaussian data, and I want to infer the mean of the Gaussian, and I have m machines and little n data points on every machine. So the classical minimax risk, I'm doing the L2 norm here just because that's more common in compression. The classical minimax risk goes as 1 over the total number of data points. This is called the parametric rate, the fast rate. It's not square root, it's just n itself. So m machines, n data points per machine. That's the total amount of data. All right, What happens if I now solve the minimax risk problem under the new constraint? Does B come into the problem? And the answer is it does. Here it is. The old classical rate appears here. Now it's multiplied by this new factor. Here's the bit rate, and then D is the dimension of the problem, the number of components of the theta vector. All right, so this is really interesting. It turned out that B didn't just appear in some way. It appeared right next to D. It's only one place it appears. Right, and this is the minimum. Okay, so this is a relationship between communication bit rate and statistical dimension of the problem. Two things that have nothing to do with each other a priori. All right, and it says to you, if you, well, so suppose I've already decided the statistical dimension of the problem. That's that the boss told me I had to estimate that vector with that many components. And now I got to say, what bit rate should I try to get? How much money should I spend on that channel? You know, well, if I choose B to be as large as D, then that goes away. That just becomes a B. That just becomes a D, and D cancels. So this tells you that you can actually get minimax risk, which is independent of the statistical dimension of the problem, if you pay enough money to get the bit rate high enough. Okay, so that's interesting. That's not part of Shannon theory. Okay, it's a link between statistics and communication. Okay, that's all I wanted to say about that. And I'm going to turn now to the last third of the talk, or whatever. Okay. Which is really the mother of all problems, which is how does statistics interact with computation? So what I've been talking about is statistics interacts with privacy, statistics interacts with communication. And there's a couple of other vignettes like this which I could do. But the hard problem I think that most of us are motivated by is how does it interact with computation? What does that mean? What does computation mean? Again, now you can look back to the historical predecessors. Didn't Turing and other people like that tell us what computation is? Well, yeah, for some purposes, but it's not the only model of computation in town. And it's not the right one for this, in fact. So for Turing, the main focus became, after Turing, exponential or polynomial. And one tape machine and two tape machines were equivalent because there was a polynomial time reduction between them. But as soon as you start to do that, and we have, other groups have tried to use that style of thinking in statistics, all the statistical constants like n and theta and d and so on appear differently in the one tape machine and the two tape machine. So it's not helpful. It's not the right model of computation. So it's probably too powerful of a model. So what are you going to do now? All right. So this is just hard. We don't have a solution. So I'm going to tell you about some of the thoughts that we've had, and then there are people around the world working on this, kind of on both sides. Not very many people, but there are people working. So here's some of the ways that have been used. This is actually mostly my group, but other people have done very similar things. So the first paper that we did on this topic was we're trying to link out computation and statistics. We put geometry in the middle. Geometry links to everything. So geometry links to computation in a very nice way. If you take a set, complicated set like a semi-definite cone, and you relax it, okay, you can go to a sum of squares problem. You can relax it further. You get a linear program and so on. And there's known runtime changes as you relax. There's theory. It tells you how the runtime gets better and better as you relax more and more and more. Okay. Mostly that theory tells you that you want to be higher up in the hierarchy, that you get much better runtimes than if you go down to the low down in the hierarchy. But that's using, for me, the wrong measure of what it means to be good. It's using a worst case geometric risk. All right. So anyway, that theory exists for various hierarchies, say like Lasserre. And so what we added was, now let's take geometry and link it to statistics. So as you relax your problems, surely the statistical risk has to go up. Okay, and it does. And we were able to quantify that for a class of problems called denoising problems. And so now you have an equation that says how the statistical risk goes up and how the computation goes down, and you just put the two together and you get a trade-off. Okay, so that paper did that. That's work with Venkat Chandrasekaran at Caltech. And it looked great, but it was limited to denoising, and we have not been able to get beyond denoising with this framework. It requires a lot of geometry and a lot of symmetries and so on. It's just mathematically, not somehow solving the whole problem. Another approach that we've been using a lot in my group at Berkeley has been to avail ourselves of ideas from concurrency control, optimistic concurrency control and sequential. Taking the database literature seriously, that's one of the beautiful achievements of the database field, and ask, well, how can I bring parallelism into statistical inference? Surely if I bring parallelism in, statistical risk should go down, right? Can I control that in some way, right? Well, if I bring parallelism in, I control concurrency, I can get the same algorithm I did in the sequential case, I can make a guarantee. right? But then I'll get a big slowdown. And the database field gives you tools for saying, well, what if I do something like, optimistically assume there are no conflicts and patch them when they rise? Then I can get big speed ups and still make guarantees. And now the algorithm question really becomes, in a statistical setting, can you find what does it mean to have a conflict? And so just to give an example of this, we did this in a clustering setting, where on multiple machines you have different data sets, and on each machine you independently try to say, well, do I need a cluster here or not? A cluster in the machine learning sense, right? So I could have completely different data on the different machines, and they just independently create clusters whenever it's happening. But I could have some shared, some of the data in the same area of the space, and I stupidly create a cluster here, and I create another cluster here redundantly. I have too many clusters. So that's a conflict. And if you can detect that you've created clusters that are close to each other, which you can then unroll the optimistic assertion and use concurrency. This is what I'm going to focus on in the last few minutes. The model of computation, which I think most people have found the most helpful, is not out of Turing complexity theory at all. It's out of optimization theory. It's out of Nesterov and Nemirovsky and others, who said something like the following. My model of computation is just that you're trying to optimize functions. Okay? And you are going to be allowed access, say, to the gradient of the function wherever you want it, and I'll give you k gradients, and k varies. All right? And now I want you to do theory on how good you can do at optimization within epsilon after you've seen k gradients in an oracle sense. No matter the smartest thing you can possibly do with those k gradients, you do them, and you get an answer. How close can you be to the optimum after k gradients? And I'll do that as a function of k. So that's oracle theory and optimization due to the Russians, and it's been extremely useful because that you can bring into contact with statistics. Now, most of the work you see in this computation meets statistics is of that flavor. I would have talked about, my favorite little topic in the recent years is the bag of little bootstraps. If you're interested, this is kind of how do you take subsamples of really, really large data sets, do the statistical bootstrap on that, Brad Efron's bootstrap, and put them a bunch of bootstraps together and get an overall confidence interval for data. I really like that topic, but I've decided I want to talk about this brand new thing called Variational Framework for Acceleration with Optimization. Let me check my time. How am I doing? Okay, I think I'm fine. Unless it's thought I'm not fine. This is work with two students at Berkeley, Andre Wibisono and Aisha Wilson. And they've really just been pondering this kind of issue for about 2 years. I'm going to show you why. This is a hard problem, and this last couple of weeks we have a paper now which I think is real progress, so I want to talk about this. And the other reason I want to talk about it, not just to brag about these students' work, is also because this word variational appears here. And so to me, variational is an underused word in computer science and statistics. It's widely used in applied mathematics and physics, underused in our fields. And so just historically, most of you probably know this, but Newton came along and did physics with differential equations, right? F equals ma is a differential equation. And he wasn't a computational person per se, but when you think about how do you bring computation into physics, well, you start with a differential equation and you have to integrate differential equations. That's the computational side of Newton's theory. So it's an integration procedure. And those tools that have been developed since that day have bleeded over into all our theories. Markov chain Monte Carlo, that's an integration procedure. And many other tools that we have learned about and borrowed are integration procedures. All right. Then, I guess it's about 100 years later, Lagrange came along and said, well, I can redo all of your physics, not with differential equations, but with calculus of variations. I can write down a functional on curves and say, find the best curve as an optimization problem. So instead of doing integration, I do optimization. All right? And if I write in the right functional, called the Lagrangian, it picks out curves which are exactly the ones you get by integrating the differential equations of Newton. All right? You get the exact same physics. And then arguably, Lagrange's perspective won out. It gave rise to quantum mechanics and so on. It was the way to go. Okay, so that's interesting for a number of reasons, but particularly because that word variational now appeared. He said, here's the solution to a problem. It's integrated differential equation. I can write that as a solution to an optimization problem. So it's essentially a functional of some kind defined on that such that the minimum of the functional is the answer. All right? Now, that became important for many reasons, largely because you could take that original functional, and it might be intractable in various ways, and you could simplify the functional. And as you simplify the function, you make it solve the problem, and the optimum might not have moved too much. And that's what's called variational methods of all kinds in applied mathematics. Another example of variational thinking is eigenvectors. So the usual way you define an eigenvector in math classes is ax equals lambda x, right? It's an algebraic definition. But another equivalent way to define it is a solution to an optimization problem. You take x transpose ax divided by x transpose x and find the optimal x. That's an optimization problem. And now you can, that particular functional is tractable, but you could have taken that and simplified it in various ways and gotten an approximate optimal. Okay, so anyway, long story short, I think the variational perspective is underutilized. I think Peter alluded to this. My early work was in probabilistic inference for graphical models, and the only tool that had been worked with other than exact methods was Markov-Giancarlo, and I worked on variational approach to that. This would be different. So this is this notion of acceleration due to Nesterov. I'm going to explain what that is. How many of you actually know what Nesterov acceleration is, just to know what my audience is? Okay. It's another reason I kind of want to talk about it, because this is brilliant work by Nesterov. This is back in the 80s, and this has kind of changed the field of optimization. And it's one of the ideas everyone should know about. So I think it's just worth talking about, even if you don't care about the variational perspective. So let me say what Nesterov did, and Nemirovsky and really this Russian school. So they were studying, let's just study convex optimization. These ideas do apply beyond that, but let's do convex for now. So we're just trying to optimize the convex function. You all know, I love these lines here. It's kind of artistic.
That's what I meant by idiosyncratic.
Idiosyncratic. So anyway, I hope you can see this is just classic gradient descent. You all know what that is, right? So I can find the gradient, and so this is the direction of steepest descent, and I'm going to now say an oracle is pick beta to find the best amount to go down that direction. So this seems like a pretty good algorithm if you're limited to gradients. Okay? You can analyze its convergence rate. It goes as 1 over the number of gradients you've seen. Okay? That's fast, but not super fast. And then the question was, is that the best you could do? And that question, there was no answer to that. There was no theory. There's no lower bound theory. And Nemirovsky and Yudin came up with this lower bound theory that said, here's an oracle theory of how well you can do. And it turns out for this problem, the oracle said 1 over k squared is the best you can possibly do. So faster. This algorithm doesn't need it. And then the question became, is there an algorithm that does? That just looks at gradients. Okay, obviously a Newton method would do it, but we're looking at it. And there it is. So this is it. This is what Nesterov discovered in 1983. So this is a little, if you've never seen this before, look at it for a minute. There is a gradient descent step here, but there's also a convex combination of two steps. So it's kind of like you are here, you're going to take a gradient step out to there. No, I always get it wrong because there isn't a good intuition here. What it is sort of that you're here, you were here, you kind of step ahead where you think your momentum is taking you, and you evaluate the gradient out there. Right? That's kind of what these two paired equations are doing. Right? So people have intuitions about them as kind of a heavy ball method, or I'm going to show you some intuitions on the next slide. But anyway, amazingly, after a fair amount of mathematics, you see that you get this rate. So this is called the accelerated method of Nesterov, and it is definitely used. Okay, there are stochastic versions of this, there's extensions to all kinds of problems. But it is a mystery.
How do you pick lambda k?
There's an algorithm for picking lambda k. All right, so, gradient methods had a comeback already in the 80s in optimization, and of course that's what all the deep learning is all based on, is gradient methods, first order methods. And they were extended all kinds of directions, not just gradient descent, but the mirror descent, cubic regularized Newton's method, and so on and so forth. They're all well understood. There are gradient descent methods and so on. Now this accelerated methods came along, and they take all these original methods and they accelerate them. They get a faster rate. Right? They're not descent methods. They will go down, they will come back up, they will go down, they'll come back up. And they're still mysterious to this day. There's, in the domain of compressed sensing, they were very important, and they're important for practice and for theory, particularly for theory. Okay, so, how do you understand these things? Well, there's an analysis tool. It's called Nesterov's estimate sequence technique, but it's just a bunch of algebra. There's really not any condition there. They kind of look like momentum methods, and that's kind of true in the Euclidean case. But it's not really true in more general cases, and there's been a whole raft of papers very recently all trying to explain this phenomenon in various settings. These are limited settings. They're either for strongly convex functions where things in some sense really get easy, or they're just for first order methods. But they're beautiful. I love this. Morris Hart has an explanation of it in terms of Chebyshev polynomials, but this is only for quadratic functions, not for general convex functions. I like this Bubeck paper of geometric shrinking. It's also very elegant, but it's strongly convex. So anyway, I'd say to this day it's very active and very interesting, but still a mystery. And if you ask Nesterov how he came up with it, he says in a very Russian accent something about, well, I'm doing a model-based approach to optimization. That's his intuition. It is kind of somehow like you're trying to get some second-order information by making a little local model, but it's not enough. So anyway, long story short, whenever you start to look at a particular methodology and try to understand where did it come from, think variationally. This is kind of going to be the story. So, okay, so the way we got started on this was that there was a very important paper from Stanford, at least in my view, that said, let's look at all these things in continuous time. Okay, so now if you're a computer scientist, you've got into computer science to avoid differential equations, but I'm telling you that you need to learn about differential equations. This is called gradient flow. It's continuous time. It's got a derivative there, all right? It just takes the gradient and goes down the gradient. There's no beta here. I don't have to worry about step sizes. This is just, there's no, no free parameter to set here, okay? And if you discretize this with just classical Euler discretization, you get gradient descent. So it's called gradient flow. Now you can analyze the convergence rate of this easily, even easier than in discrete time, and you get 1 over t. Not 1 over k, because we're in continuous time, 1 over t. All right, anyway, Sue, Boyd, and Candace at Stanford wrote this nice paper in which they took the accelerated method that I had a couple of slides ago and took the limiting step size going to 0, and you get out a differential equation. And it looks like this. So it's a pretty important differential equation, I think. It's second order, so you wouldn't be surprised that this thing's going to oscillate. It's not homogeneous. There's a t here. Okay, so the damping is going down over time. And it has the gradient appearing here. Okay, so that's that equation. So then they were able to do some theory on this and analyze its oscillation and stuff. So this gave some real insight. And then it was extended to mirror descent and some various extensions. All right, now this really triggered in our thinking kind of the notion that, well, behind a differential equation, there's got to be a variational principle. Okay, what is the variational principle? And so will that make us go further? So that's what we're going to provide here. So I'm going to write it up on this next slide. Here it is, right here. So this is an object we're calling the Bregman Lagrangian. So let me just show you some of the pieces here. This is called the Bregman divergence. That's the first term of this thing. Okay? These are just kind of rate constants. Forget about them. The important part is right here and right here. So this is called the Bregman divergence. If you haven't seen it before, it's just a measure of distance between a point x and a point y. You have kind of a distance generating function h. You drop a tangent right here, and that difference right there is the Bregman divergence between x and h. So it's the extra discrepancy. If h is a quadratic function, this is just Euclidean distance, a crazy way to define Euclidean distance. But in more general terms, that's the Bregman divergence. Okay, so this is a Bregman divergence between x perturbed by a certain amount along the the direction of time change with a rate of some kind, and x. Okay, so there it is. That term, you subtract off the actual function f. There's no f here. This is just about the change, and this is about what you're trying to optimize. Okay, so f is now. These functions right here are just kind of rates, and we have to set them in particular ways to get particular algorithms. That's the next part of the story, or the last part of the story. Now, if you take the Bregman divergence, if you take h to be quadratic, the Bregman divergence just reduces to this, and that looks like a kinetic energy. So it looks like physics. This is like a kinetic energy minus something like a potential. This looks like a Lagrangian from physics. Okay, so now let's talk about these gammas and alphas and betas. So it turns out, as the theory is going to show us, to get fast rates, these accelerated rates, there's only really one free rate parameter here, it's alpha. So if you set beta according to this equation and gamma according to this equation, then you will get these fast rates that I'm claiming that we're going to get out of this framework. So it really is just now alpha that has got to be set. Okay, so all right, so here it is again. I've written it up again. There's our Bregman Lagrangian. Now, this is just classical calculus of variations that Lagrange would have recognized. You take that object right there, which is a function of time, and you integrate it to get a single number, a functional. And now you find the curve, which minimizes that functional. So this might be the curve right there. And this is a test functional, which has a smaller or a larger value of the objective. Okay? And calculus of variations, you can do it numerically with dynamic programming, or you can do it analytically with what are called the Lagrange equations. This is just the continuum version of set all the partial derivatives equal to 0. That's all it is. Okay, so you just get this equation. This is just a derivative of this functional up here, and this is a time derivative. This is just a differential equation. It looks kind of complicated, but it's just a differential equation. Okay, so let's actually plug it in and get the differential equation. Here it is. This is our master equation. Okay, so from that Lagrangian, we're getting a family of differential equations, all of which are second order here. All right, they're non-homogeneous with some kind of rate out here as a damping, and there's a kind of a complex thing here which multiplies the gradient. Okay. All right. So what I'm going to argue, and I want to end fairly soon. I want to sort of suppress some details here, but that this equation generates all known accelerated methods. Okay. Yeah. The non-Euclidean, non-Euclidean cases, the mirror version, the composite versions, and so on. So that gets really interesting. So in fact, let's see that it generates the one, the Sue, Boyd, and Candace one. Let's see. So before we do that, let's actually get the convergence rate of this. So the convergence rate of this, there it is. There's the optimum. Here's where you are. Turns out to go as O to the e to the minus beta t. Okay. So it looks exponential. That's kind of surprising. Of course, one continuous time, anything can happen. But the first point to make is that the analysis of this in this complete generality is trivial. You write down a Lyapunov function right there, you take its first derivative, and you want the first derivative to be negative. This thing right there is just the condition that this first derivative is negative. So it's a two-line proof for convergence rates in complete generality. That's much easier than in discrete time. Okay, so now let's try to set this alpha parameter in some way which gives us real algorithms and not just kind of mathematical fictions about moving along curves. Things that we can actually discretize on a computer. Okay, so we don't really expect exponential rates. We expect polynomial rates. So let's make that explicit by having a parameter p, having alpha be log p, and then go as logarithm in the time. Okay, so we're going to parameterize a family of rates given by p. All right, so in particular, when you put these, and then beta and gamma are determined by our choice of alpha. When you put these back in that equation on the previous slide, you're going to get out rates which go as 1 over t to the p. Just the beta is right there. You know, you plug it in, you get t to the p. So that's kind of the familiar rate, 1 over t squared, that we're kind of expecting to get. So this might be the family we should be studying. All right, so we plug those back into the master equation. We get this differential equation. And there we're getting this kind of now simpler expression right there. Okay? And in particular, if we set p equals to 2, we get that equation. You get Sue, Boyd, and Candace. Okay? All right? And it has this 1 over t squared convergence rate. We're on the right path. We also get this mirror descent, which I didn't discuss, but a parallel result of mirror descent, and we get their convergence rate as well. Okay, so we're kind of on the right path here. And now the question is, this begs the question, what if p is 3 or 4 or 5? And it turns out that all those algorithms exist. And so this is an actual discovery that you can get order t to the arbitrary, t to the p rate. And I'm going to show you the algorithm using those things. Okay, so the acceleration goes further than had been realized. All right, but now the p question, the last one, is how do you discretize these Euler-Lagrange equations? So, you know, when you do fancy differential equations for like climate modeling or fluids or whatever, that is kind of the core question. How do you know the equations? How do you discretize them? All right, so that's where kind of the magic of this comes in, or the strangeness. If you just try to discretize this in a naive way, doing what are called first order Euler steps things, then you get out a discretization which fails. It fails in two ways. It's not stable, and secondly, you lose the fast convergence rate. The acceleration phenomena vanishes. Okay, so here it is, and again, I'm kind of trying to suppress math here, but if you just do Euler discretization, you get out, from the differential equation, you get out some difference equations, you put them on a computer, they converge in, and then they go shoot off to infinity. They're unstable. And here they are, converge in, shoot off to infinity. Not a good algorithm. All right, so now you think, okay, is there better ways to discretize, or is this just kind of a family of things you can't discretize, like shock waves or something? All right, and if you try to kind of use more fancy things out of the usual differential equation textbook, they also don't work, right? But if you use a new technique, well, I actually don't think it's new. I suspect this has to do with what's called symplectic geometry. But if you introduce an auxiliary sequence y, you put in a new equation, a y here, and you get three equations out of this, and y has got to obey some particular property, all right? This is inspired by Nestorov's thinking. Okay, Nesterov had these three sequences. We're just kind of mimicking what he did now as a discretization methodology, not as an optimization methodology. When we do that, we actually get out an equation which has provably now the discrete time rate 1 over k to the p. Okay, so it doesn't oscillate, or it does oscillate, but it doesn't go up to infinity. It's stable. and it actually has the fast rate. Okay, and let me just, I think I wanted to give it a slide we actually show this. I want to finish up here. Yeah, here it is right here. So this is for the arbitrary value of k. It's 3 equations now instead of just 2. And it's kind of a convex combination of kind of some mirror descent kind of thing. So anyway, the theory tells you that if you discretize in this particular way, you get out these accelerated rates for arbitrary values. So I want to close up now. I think I'm done. So just to kind of summarize, classically people did understand gradient flows. They understood high order gradient flows. They had slow rates. And if you did this then in discrete time, you got gradient methods which had slow rates. What we've shown here is that this new equation generates in continuous time fast rates, and there's a discretization procedure which preserves the fast rates in discrete time. So that's the novelty of this paper. I'm going to skip over some. Now you can study the Lagrangian itself. It has some properties. I'm going to skip over that and go right to the final slide. Which here's this new thing which I think is interesting, worth studying. It has some statistical interpretation. You had to hark back to the first part of my talk. And it generates these rates in an understandable way. There's kind of a principle here. It turns out if you want exponential rates, you can actually get it if you have uniform convexity, the stronger convexity property. You can actually achieve those with another class of algorithms. And now there's a lot of work going on trying to understand this Bregman Lagrangian, its kind of physicsy kind of properties, symmetries, gauging rooms, and so on. And then wherever there's Lagrangian, there's always a Hamiltonian here with a plus sign instead of a minus sign, and this object is worthy of study as well. Okay, so some apologies for some math. That's recent work that I think is real interesting. So I thought as in a research audience, I would bring it to your attention and let you know about the whole Nesterov style of thinking. So I'm done. I think I had, this was back to the main thread of the talk. Hopefully the message is clear that big data is real, it's scientifically interesting, it's in addition to all the systems building and all the deployment in real life scenarios and public policy issues and so on, all the things, the $1 trillion economy, all that, it is going to change the face of computer science and statistics. The next 100 years will be different because of the data science era. So it's the first time in my career I think I could say that. I think I see this phenomenon which is reaching everywhere in academia and having an impact on industry. So especially for younger people in the audience kind of looking for things to do, you're lucky. There's so much to do right now. This is the time. This is where the new terrain will arise to kind of help us with computation. The new Kolmogorov will arise. This is kind of new conceptual ideas are needed. So thanks.